We're going to find a derivative here for y equals e to the x over 1 minus e to the x. Because we have a quotient, we're going to use the quotient rule. I'll identify the numerator e to the x as u. And the 1 minus e to the x in the denominator is going to be v. Then u prime is equal to e to the x, and v prime is equal to negative e to the x. As a reminder, the quotient rule is u over v prime is equal to u prime v minus uv prime divided by v squared. And you'll notice that when I write my u's, I put a little tail on them. My v's don't always have a sharp point. They do when I'm paying attention, really. But that tail distinguishes my u from my v. I highly encourage you to make sure that your u doesn't look like a v. And sometimes I see a u and a v, and they don't really look different. And we're going to be using a lot of u's and v's in this course, so I'm going to need you to pay attention to that. Now, y prime, using the quotient rule, u prime v minus uv prime over v squared is going to be e to the x times the quantity of 1 minus e to the x minus e to the x times the negative of e to the x, all over 1 minus e to the x, the quantity squared. I recommend generally not expanding out the denominator pretty much anytime. Distributing in the numerator, we get e to the x minus e to the 2x plus e to the 2x, and that's going to be over 1 minus e to the x, the quantity squared. E to the 2x is subtract out, and so y prime is equal to e to the x over the quantity of 1 minus e to the x squared. Now we're going to look at an integral. It is the integral of x squared e to the x cubed dx. We're going to do what we commonly call a U-substitution. U is equal to x cubed, and so du is equal to 3x squared dx. The way I like to handle this is I look at what we have and look at what we need. So for du, we need 3x squared dx. I have the x squared dx, and so I'm going to multiply inside of the integral by 3, and outside I'm going to divide by 3. Ultimately here we're multiplying by 1. So that gives us 1/3 e to the x cubed plus c, because essentially what we just did was we created an integral that looked like 1/3 times the integral of e to the u du, where du was what replaced 3x squared dx. And of course the integral of e to the u is e to the u. Now let's look at a couple of limits. First, the limit as x approaches negative infinity of 1.001 to the x. What I notice here is that the base is bigger than 1. Therefore, the graph of this function, without really giving any details here, although I'll label the x and y axes, is that of exponential growth. We're looking at the limit as x approaches negative infinity, and so we're seeing what happens to this graph toward the left. Because it is asymptotic with the x-axis on the left, we can see that this answer is going to be 0. Next up, we've got the limit as x approaches 2 from the minus side of e to the 3 over 2 minus x. We'll look at the exponent here, and we'll note that as x approaches 2 from the minus side, so numbers less than 2, 2 minus x approaches 0 from the positive side. Therefore, 3 over 2 minus x approaches infinity as x approaches 2 from the minus side. We have a denominator that's going to 0, but is remaining positive. If the exponent is going to infinity, then e to that exponent is going to go to infinity. For the visual here, again, just a quick sketch, and we're just going to consider y equals e to the x this time. As x approaches infinity, we can see that the output approaches infinity. As you saw here with these two exercises when we were looking at limits, I referred to the graph of the limit each time, or the expression, I should say. And I highly recommend that when you're dealing with limits that involve exponential functions, that you do turn to the graph. It can be make things much easier to think about if you know how the graph is moving.